In this video here, we're going to take a look at the trapezium rule. Now, the trapezium rule is a numerical method that allows us to approximate the value of an integral. And this is useful as it allows us to obtain an approximate value to an integral that we may not be able to integrate using the standard methods covered in A-level maths. So to start with here then, let's just actually introduce the trapezium rule and discover how we can derive it ourselves. So to get us started here then, let's just consider the following curve, y equals f of x, okay? And we can also see a diagram then of this curve, y equals f of x. Now the question that we want to answer here then is how would we find the area under this curve, y equals f of x between a and b by using the trapezium rule? Well, if we want to find the area under the curve, y equals f of x between a and b by using the trapezium rule, the first thing that we need to do here then is start by splitting the area up into n equal strips, where each strip will have a width of h, and h is equal to b minus a over n. And if we do that here then, we'd get something like the following. So all we've done here then is split this interval up, ab, into n equal strips. So each strip here then will have a width of h, where h is equal to b minus a over n. And we can also see here then on our diagram, we have y0, y1, y2, y3, so on and so on, all the way up to y subscript n minus 1 and yn here. So what we now have then is n trapezia, and what we can do is we can find an approximation to the area under the curve by finding the sum of the areas of the trapezia. So in that case then, the area under the curve is given by the following. So the integral of y with respect to x from a to b is approximately, so we get a half h times y0 plus y1. So this here then, let's do that in a different color. Let's do it in, we'll do it in green. So this here, this is the area of the first trapezium. Okay, that's this trapezium here. So now for the second one, let's do that in blue. We've got a half h times y1 plus y2. So this here then, this is the area of the second trapezium. Okay, and basically all we need to do here then is just find the area of each trapezium. We add those all together. What this gives us then is an approximation to the original integral. So what we can also do here then is factorize to simplify this result and obtain our desired result. So if we do that then, the integral of y with respect to x from a to b is approximately the following. So we get a half h times y0 plus yn. We also have two lots of y1 plus y2 plus so on and so on. Apologies, by the way, there should be a plus there. Let's quickly amend that. So plus y subscript n minus 1. Okay, so a half h times y0 plus yn. We also add on two lots of y1 plus y2 plus so on and so on, all the way up to y subscript n minus 1, where again h is equal to b minus a over n. So what this gives us here then is the trapezium rule, and the good news is that this result is also given in your formula book, so it's not something that you do need to memorize. Okay, so there we have it. That gives us the derivation then of the trapezium rule. So an important consideration here then when working with the trapezium rule is whether our approximation has produced an overestimate or an underestimate. And here's what you need to remember then. So convex curves produce an overestimate. And this diagram here then demonstrates a convex curve. So we've got our convex curve here then. We're using the trapezium rule, and as we can see, or hopefully it's quite obvious, this has produced an overestimate because, let me just do this in a different color. So if I do it in light blue here, for example, right? As you can hopefully see here then, the diagonals of the trapezia here are actually above the curve, okay? I kind of sketched that in there. This little bit here is above the curve, and same again here. So what does that mean then? Well, the area approximated using the trapezium rule will be greater than the actual area under the curve, because basically we've got a little bit of the trapezia, so a little bit of the area of the trapezia above the curve, and in that case then we have a little bit extra that isn't actually included for the actual area. Okay, so hopefully that makes sense there. And you also need to remember then that concave curves produce an underestimate. And this diagram here then demonstrates that concept. So again, I've got light blue, so let's just do it here again. I've got this little bit here that isn't actually included. And same again here. So what does that mean then? Well, what that means here is the area approximated using the trapezium rule is less than the actual area under the curve. Okay, so these 2 points here, really, really important. And you will get asked that within exam questions. So please do make a note here of these 2 points. Okay. So to finish with here, then let's just quickly discuss how we can improve the accuracy of the trapezium rule. So one way that we can improve the accuracy of our approximation is to increase the number of strips. And what this does here then is this divides the interval into smaller strips which better follow the shape of the curve, hence giving us a more accurate estimate. And this is demonstrated then by the 2 diagrams below here. So this approximation on the left uses 4 strips, so 1, 2, 3, 4. And this approximation here then on the right uses 10 strips. I won't bother counting those out, but I promise you there is 10 strips there. So I'm hoping it's quite obvious based on the 2 diagrams here, but basically when we only have 4 strips here, as we can see, right, and let me just do this in a different color. Let's do it in green. What we can see here then is we have these 2 parts that are actually above the original curve. Okay. And that isn't evident here for the second approximation, which has a greater number of strips, right? And again, the reason for that is because what we've done here then is split the interval up into smaller strips, which better follow the shape of the curve. So in that case then, we obtain a more accurate estimate. So it is important then that you are aware about how we can improve the accuracy of the trapezium rule. And this does often come up in exam questions for 1 mark, just asking how can we improve the accuracy of our estimate. Okay. And that's all you need to say then, just increase the number of strips. So there we have it in terms of an introduction here to the trapezium rule. There is quite a few different things going on in terms of the introduction here. So feel free to kind of go back, make notes, kind of jot down everything that's important to you as you work through the video. But other than that, we don't need anything else here. So I think the best way to demonstrate the trapezium rule here is to just work through 1 practice question together. So let's just get started then with this practice question here. So for this question, then we're given that y is equal to the square root of 4 to the x plus 1. And for the first part of this question, then part A, all we need to do is complete this table here, given the values of y to 3 decimal places. So nice and straightforward to begin with here, right? So when x equals 0, what is the value of y? So y is equal to the square root then of 4 to 0 plus 1. Well, 4 to 0 is just 1, so we get the square root of 2. So obviously, just use the calculator here, right? So in that case then, what we get here is 1.414. Okay. Moving on then, when x equals 1 here, what do we get then for y? Well, y is equal to the square root of 4 to the 1 plus 1, which is just the same as the square root of 5. So to 3 decimal places, then what we get here is 2.236. Okay. And then finally here, when x equals 2, y is equal to the square root then of 4 squared plus 1. That's just the square root of 17, which gives us 4.123 there. Okay. And there we have it then. So as we mentioned, right, nice and straightforward here for part A. There we have it. That is our solution. So now for part B then, let's do that up here. So for part B then, it says use the trapezium rule with all the values of y from your table to find an approximation for the value of this integral here. So to begin with then, let's just actually state the result then for the trapezium rule. And don't forget here that this is given in your formula book, but let's just state it on the screen here, just so we can see it as we work through the question. So the integral then, so the integral here of y with respect to x from a to b, so from a to b is approximately, we get a half h or h over 2, whichever you prefer, times by, so we have y naught, that's our first y value, plus yn, our last value, plus 2 lots of everything else. So 2 lots of y1, plus y2, plus so on and so on, all the way up to our penultimate y value, which is y subscript n minus 1. Okay, like so there. So this result here then is the trapezium rule. And don't forget here as well that h is equal to b minus a over n. Okay? And h here is actually just the difference then in our x value. So for this question here, h is just simply 0.5. Okay? We'll make a note here that h is equal to 0.5 there. So if we put that all together then, we can now find an approximate value for this integral here. So the integral of the square root of 40x plus 1 with respect to x from 0 to 2 is approximately, so if we now just use the trapezium rule here then, we have h over 2, so that's going to be 0.5 divided by 2. So 0.5 over 2. We then times this by the following here. So we have y0, which is our first y value here. So 1.414 plus our last y value, yn, which in this case is 4.123. So 4.123 there. And then we have plus 2 lots of everything else. So 2 lots of, so 1.732 here. Like so. 2.236. And then finally, our penultimate y value here, which is 3. Okay, like so. And at this point here then, obviously just use a calculator, right? So if we do this correctly here then, rounding our answer to 3 significant figures, what you should get then is 4.868 there. Okay. And there we have it. So like you can see, using the trapezium rule is quite a straightforward process, and it does allow us to find the approximate value then to sometimes, in this case here, it's not the most challenging, but sometimes quite tricky integrals. Okay. But there we have it then. So that gives us the solution, the one practice question for this video here. And that actually brings us to the end then of this video here on the trapezium rule.